goes up?
Yeah.
Okay, so we have a frame here. It is built of 3 different members. A, B, C is one piece of metal. C, D, E is another piece of metal, and B, D is another piece of metal. And I'm asking you if A, B, C is a 2 or 3/4 member. And on Tuesday, what we discussed is when you have a member that only has the forces and reactions concentrated on the ends, it's considered a 2/4 member. So in this case, is A, B, C a 2/4 member? No, why not?
Because there's three
Because the force
forces.
is in the middle.
Because there are, give me be specific.
Forces at B.
Yeah, there's a connection at B, which means there are reactions at that support, so there are forces at B. Okay, so it's a 3/4 member. How about BD?
Yes.
Yes.
2/4 or 3? 2/4 member. How come?
Because there's only forces and reactions at the end.
Right, because there are supports at the end, which means there are only reactions at the end, there are only forces at the end. Eric?
What if you had a force connection on A, B, C, would it be a 4 force?
Yeah, that's where we're going to the next one. Good. Okay, so now we're looking at members C, D, E. So what's going on at C, D, E? Well, I have a connection at E, I have a connection at D, I have a connection at C. And then what's this thing on the right? What's this thing? Can you even see it? Kinda light.
Distributed load.
It's a distributed load. And how could I take a distributed load and make it a point load? I multiply the force per unit length times the length, and since it's rectangular, I know it would be in the center, right? This would be L over 2, L2 over 2. So in the end, is C, D, E a 2/4 member?
No.
No. Is it a 3/4 member?
No.
No. Why not? Because there's another force there. What is it? It's probably, I would probably call it a 4/4 member. But I've never seen something referred to as a 4/4 member, or a 5 or a 6. The reason why is whether it's a 3, 4, 5, 6, 10, whatever force member, you treat it the same way. It's only 2 force members that you treat differently. So how do we treat them? Let's draw the free body diagrams. So based on the fact that we know that 2 force members only carry axial loads, what's axial mean? It's along the axis of the member. Draw free body diagrams for A, B, C, for B, D, and for C, D, E. So here's C, here's D, here's E, here's D, here's B, here's A, B, C. So of course, it's important, I need to make sure I put my axis on here, right? And I need to make sure I put distances. I'm noticing those on quizzes that you guys are still forgetting to put axes in, and you're still forgetting to put all the distances in. So remember to put those in. Okay. And here, we're just gonna go through this quickly. So let's go around. Santiago, let's do A, B, C. Tell me what I need to put on here.
There is AX and AY,
And why?
because there is a pin there.
A pin. These are reactions at a pin. Okay.
And then there is a tension, I believe.
It's not a tension, it's actually a metal.
All right.
It's
so
metal.
there's BY and BX.
Actually, no, because it's a 2 force member, let's jump ahead to BD. We jump ahead to BD? This is a 2 force member. If it's normally, we would put, I'm gonna do it in pencil. I have an eraser. Normally, because it's a pin, I would have a BX and a BY. I'm writing in pencil because I'm gonna erase it. I would also have a DX and DY. And then I would have the equal and opposite here. But we just learned that on a 2 force member, we know the direction of the force that's going through here. It's axially. So you decide if you want it to be compression or tension. I'm just going to draw it in this way. which is what, tension or compression?
Compression.
Compression. So this is, I'm gonna call it BD, and is this BD too?
Yeah.
Equal and opposite, so then what am I drawing here?
This and then
BD and BD. So this is awesome that we know on two force members, we just reduced it from 4 unknowns, BX, BY, DX, DY, to how many? To what? To a BD. Right? So we want to remember what a two force member is, because what does it do? Decreases the amount of work we have to do. Right? I don't want to solve for BX, BY, DX, DY, and then find out that the Y's are 0 and BX is equal to DX. I don't want to have to take all that time. So if it's a two force member, we know it's axially through.
This is a problem from the quiz that we took last time.
Kind of.
Kind of?
Yeah, it's a little bit different.
Oh, okay.
I just drew something quickly.
Oh, okay.
Okay? So, all right, what else do I need to have in here then? Lonnie? Or did you do the B's? No. Okay. What else do I need?
You need CX and CY.
CX and CY. And what about over here? How would I draw it?
CX would go that way, CY would go that way.
Right. Sarah, anything else?
Not on that one,
Okay. Want to go to the next one?
yeah.
What else do we have?
So then you're just like the E,
Right?
and it's in the DX and
Actually,
Y. Or
this
is it a wheel?
it's a wheel.
Oh, the normal.
Just a normal. And there's one more, the external force. Yeah. I heard somebody say yeah,
Oh, yeah.
whatever that happens to be. Okay, does everybody understand the concept of the two force member now?
You have to write the distances?
Yes, but I didn't write them. But I have to write them, but I'm not gonna write them, because I wanna go on to the next thing. Because you can't do moment equations unless you have the distances. Right? Once, everybody listening, once you draw your free body diagram, there is no reason for you to go back to the initial picture. If you do some of the moments and you can't find the distances on your free body diagram, you in your head go back to the original drawing to get your distances, but it should be an indication, oh shoot, I forgot to put the distances on here. Daniel,
So since you said BD is metal, you
well, it could have been a popsicle stick.
so I guess I'm having trouble seeing why BD. You know BD is gonna have to be going towards B. Like it's not.
If we
it's not
did-
tension.
If we left, oh, I don't know if it's going this way or that way.
Oh, okay.
Yeah, and maybe intuitively,
I mean, how you drew it makes sense, I guess, because there's a force going that way.
but it
right?
doesn't matter, I could have
Okay.
drawn it going out instead, and then if it was
Negative.
going in, I would have got a negative.
Okay.
I just know I'm drawing it one way, and it's along the axis.
Okay. Thank you.
Would you need like an angle or like another distance up there?
Yeah, we need distances and angles, but I didn't draw that because that wasn't what we were worrying about. We were worrying about two force members. Too bad Rachel's not here. But I'll give her some extra points because she found one of my errors. Okay, so we're gonna do it on here, and then I'm gonna show you where the mistake I made. All right, can everybody see this picture? The other thing on frames that makes it difficult, well, actually, not other thing that makes it difficult, because knowing about two force members doesn't make it difficult, it makes it more easy, right? Okay, so right here, do you guys see that I have three things connecting, right? One thing is here, another thing is here, and another thing is here. Whenever I separate things, I have to account for it by what? Reactions at the supports. So when I take this whole thing, this green member and this green member together, and I separate it from its main support, I have to account for it. And it's a pin, so I put an AX and an AY. Everybody happy with that? Then, when I separate the two greens, when I separate the greens now, I have to account for those also, right? And how did I account for those? By AX prime and AY prime. Do you agree? Every time you separate something, you have to account for it. But what Rachel pointed out, everybody look up here, I didn't have the AX and AY drawn. And she realized that when I put these two together, what happens to the primes? They cancel, and then do I have the same free body diagram of that as that? No. If I don't have the AX and AY drawn, and I put these two together, the primes cancel and I have no force, which means this and this would not be equal to each other, but they are. So I have to remember to put in the AX and I have to put the AX and the AY on one of them. And which one do I put it on? I always put it on the one that's drawn on top that you could see. Oh, yeah. So it would have been drawn like this. This was the one that was on top, and this one was underneath it. So I have a habit of always drawing it on the top.
I'm not seeing the matchup from AXAY and then you're adding it again.
Okay, so let's start with it all separated.
Because there should be, the AX should be going the same way, right? You have the AY coming out.
Oh, yes, yes, good point. Good job. Okay, Chris, you're getting some points too. Oh, AY was right.
Yeah.
Good job. Does everybody see what Chris said?
Yeah.
That when I take these two and I put them, add them together, they need to equal this. In order to equal this, we have to have a sum total of AX in the negative direction and an AY in the positive direction, correct? And then, when I take these two drawings and add them together, there's nothing here because the force inside is internal.
So you could put the AX, AY on either the red one or the blue one?
Yeah, but I always put it on the one that's in front, and that it works out all the time.
Is there any reason for that, or?
I didn't really think about it. I just always have done it that way, and everything's worked out.
Okay.
But we know it could only be on one of them, right?
Yeah.
You could try one of the problems, the frame problem that's due when we get back after the test. You could try it and see, do it both ways and see if it works out. So in the end, the total resultant force that's on the pin is a sum of AXA and AX prime and AY and AY prime. Because that's what the pin is experiencing and that's what we have to design it for. So now, pull out the sheet from Tuesday. Check me, there's something wrong on here. What's wrong? What is missing? I shouldn't say wrong, what is missing? Okay. The axis, the distances. So what about the forces that are drawn?
You're missing your AY, or your AY and your
AX and AY. So I went from the original sketch to pulling the whole structure away from A and I put in AX and AY. Then I took these two members, and I separated ABC and ADE, and one of them, you can tell which one's on top, right?
Yeah.
So this one I should have drawn AX on it and AY. And down here, the same thing, AX and AY.
If you ended up, crossing out 3.5.
Yeah, we didn't do it, but just in case. Okay, so that's what I left off. But I I'm hoping you went over this, and I'm hoping that you went over the solutions I sent you, because here's more practice problems. But this turns out to be correct. Let me see. So on the email for the solution, same thing. I have AX and AY missing. AX and AY missing. And then when I went through and did the problem, I redid it, I added this in here, that there should have been an AX and an AY, and there should be an AX here. Did any of you print this out when I emailed it to you? No? Okay, so when you go through the math now, that's on there, everything here is fine. When you get to this free-body diagram, I should have had AX and AY in it, which means AX should have been in the sum of the forces of the X. And AX prime turns out to be 0. Maybe I should email this to you, because I'm correcting it. Yeah?
Yeah.
Okay. And that's it. Everything else turns out to be fine. So yeah, let me email you that solution that has the correction on it. I'll do that. Okay, so has anybody started the frame homework? Okay, I would suggest starting it, even though it's, not on the exam. These types of problems are just like regular problems. It's just two force members, and the whole idea of having three things together is kind of a new thing that's introduced in frames, but that's the only thing.